Okay, so this is lecture 6, and we will actually talk about the optimization models. But before we do that, actually, I want to kind of go through the second question of the homework, and then kind of have a quick discussion on how to solve that question. This is due to, like I received a couple questions from the team members, so I thought that maybe it would be helpful to go through this question and then work on it. And this should take not so much time. And then this will also be kind of an intro to the next topic, which is going to be, more real life applications of optimization, plus also, like sensitivity analysis, those type of topics. So here in this question, it's about this is a manufacturing company. They are basically manufacturing desks and chairs. So they have two types of products, and each desk basically consumes some number of other parts, basically. For example, for desk, it uses 4 units of wood, and each chair uses 3 units of wood. And then each of these items, these are like products, brings some profit. One of them brings like $400, the other one brings like $250. And of course, there is some restriction, which is basically there's some availability on the total amount of wood that we can use. And then at the end, using this available limited resource, the idea is like finding the right number of desks and chairs to produce so that we can maximize the profit. Although this problem is like simple, a little bit more complicated form of this problem is used actually in real life applications, and we will kind of go through them. But then just to give you a sense of like how to kind of how to use like SAS to solve this problem. Let me just quickly open this and okay. So basically, in this problem, the idea is like identifying what is the decision variable and what is the like the constraints and objective function. As you guys remember, we will use PROCOP model. Okay, so PROCOP model is a procedure by SAS, right? And basically it solves optimization problems. And in this problem, we have 2 things to decide: how many units of desk to manufacture and how many units of chairs to manufacture. So because of this, I'm going to define this 2 decision variables, and I'm going to say, call them actually desks and chairs. Okay. Of course, both of these variables needs to be positive, as you guys remember, like because this is like we cannot produce negative number of chairs, right? So we basically are gonna put non-negative constraints here. So one thing I do actually, sometimes I don't remember the syntax, so I kind of run and see whether everything goes through, and it did. Like the one that I don't remember is like whether it's a comma or a space between decision variables, and it seems like comma is correct. So, and then the second thing to find out is actually the objective function, and in this case, this is a maximization problem. So we want to maximize the profit, and here the profit is basically the profit that each desk unit brings and the profit that each chair brings. And when we look at here, the profit, it says basically for each desk, we are making, okay, I'm going to just copy paste here. We are making $400, and then each chair we are making $250. Okay, so basically this is it, right? The objective function. This is actually, I'm not going to call it F. I'm going to give a more meaningful name so that later when you look back to the code, it's more meaningful. And then there's actually only one constraint, which is the limitation on the woods available. So, so we need to define a constraint basically, and then this constraint basically is how much desks are going to need the wood and how many units of wood chairs are going to need. And it seems like each chair needs 3 units and each desk needs 4 units. You guys can see here. Okay, so then the total consumption by desks are 4 multiplied by the desks, and then for the chairs, it's basically 3 multiply chairs, right? And then we know that there's an availability here, constraint here, and we cannot exceed 2,000 units, and that's it. Okay, and then basically we put a solve statement so that the op model knows that it needs to solve this problem. of course, when we solve, it's going to solve and it's going to tell us the optimal profit. But then we may want to also see how many chairs, right? Because here the action is like, if you want to execute this plan, you need to know how many from each. So because of this, let's kind of print them. Hold on. Okay. So basically, it seems like the objective value is this much, right? It's like $200,000. And the optimal plan seems to be manufacturing 500 units of desk and not manufacturing chairs at all. So I think this makes sense because the desks makes more money, right? If you need to use, and you have only one resource, which is the wood, then in that sense, why not try to use it with the desk for desk? But of course, if each desk consumes too many units of wood, then this would change, right? And then actually we can change this here. So as you guys remember, each desk basically consumes like 4 units of wood. If it consumes like 20 units of wood, then it may become too expensive. And at that point, maybe we will start manufacturing chairs as well. And you guys can see now, actually chairs is more profitable. So just to repeat what I did here, so at the beginning, the actual problem was each desk consumes 4 units of wood, and each chair consumes 3 units of wood. And with that given, what we found is like the optimal solution was manufacturing 500 units of desk and 0 units of chairs. Because compared to what the desks are consuming, and then when we compare it with the profit that it brings, it seems like it is worthwhile to not manufacturing chairs at all, but just focus on desks. And then on purpose, I make manufacturing desks more expensive by saying that each desk is going to consume like 20 units of wood. Then at that point, if I run this one, then the solution was no desks at all, but chairs. Okay, so then at that point, what we know is like, although desks bring more profit, but because it consumes so much wood, it's not profitable that as much anymore. So which means that let's focus on chairs more. So as you can see, depending on the parameters given on the problem, things may vary basically. Okay. So let's do this one. Do the sensitivity analysis to see what happens to the decision variables and the total profit when the availability of wood varies from 10,000 to 3,000. So actually, I'm going to touch this topic a little bit on the allowable decrease and increase in the coefficients on the right-hand side, and that's going to actually help you. But one thing that I'm going to mention, SAS actually in the past has this feature of reporting these numbers, but at this point, there is not a straightforward way to do that. So which means that if you want to use SAS for this, you may need to run this problem multiple times. Basically, let me convert this problem to go back to its original form, which is like each desk consumes 4 units of wood. And one second, let me stop sharing for momentarily and I will come back. Okay, I'm still on the line, but I'm just not sharing. Because it seems like my chat window is open and it's kind of making this.
Dr. C, so question,
yeah, go ahead.
Why you said that you have to run multiple times? If the constraints are constant, at a particular point, you will always be either in a profit or like you would always know that the desks are always going to make more profit than chairs because they're always going to use four wood compared to 3.
Sorry, can you repeat the question again, Puneet?
You mentioned about running the models again in SAS, right? To get the optimal result. Why is that?
So here, basically, it's asking that availability of the wood, originally we have this many units of wood available, which is 2,000, right? Now it is asking, let's say that the availability of the wood changes from 1,000 to 3,000. So which means that actually this means, like we need to understand what the optimal solution is going to be when the right-hand side is 1,000, 1,100, 1,200, 1,300, 1,400, 1,500, like kind of increments of 100 units. And each each of them becomes a different problem, right? The good thing is like, I'll also address this in Excel, like actually there is a concept of allowable increase and decrease. So basically, there's a range of coefficients on the right-hand side that if you change range, the right-hand side in this range, nothing is going to change. Okay, and then because if that output is given to you, then you don't maybe need to run as many. You may still need to run some because some of these may be out of range. Okay,
Right.
but you may not need to run as many. So that's the. But then let me demonstrate in SAS, because SAS, maybe because it's not a very used feature, it seems like they stopped actually supporting that, and they don't have that anymore. Okay, I'm going to indent. This indenting is kind of a preference on the coding. There's nothing, no implication on how the code runs. So basically, the way that I'm going to do right now, it's asking basically the total profit and the decision variable. The nice thing about SAS, actually, you can keep the same PROCOP model and quit, and in between, you can run multiple optimization problems. Okay. So what I'm going to do. So I'm going to actually make a name for this constraint because I want this constraint not to be used in the second iteration. So I'm going to say maybe, because this is scenario 1, right? This is scenario 1. So I'm going to say this constraint name is this. So this is kind of a label. Again, it doesn't change anything about the optimization. It just gives a label. Like profit, for example, is a label. This is going to be labeled too. So what we are going to do is we are going to actually, each time we solve a different version of this problem, we are going to drop this constraint. Okay, we are going to say drop it. And then we are going to introduce a new one, but this time with a different right-hand side. And then we are going to solve and print. Okay, so what optimization? So basically we have, as you guys remember, 3 different components of an optimization problem: decision variable, right, which we defined here, objective function, which we defined here, and then the constraint, which we defined here. Okay, whenever we say solve, basically these 3 things will be taken into account. So whenever I drop something, next time I solve, the thing that I drop is not going to be considered anymore, but the rest still will be valid. Which means that once I define a new constraint, and I'm going to name them separately so that easy, but we can actually name it same because we dropped it. But let's name it separately. Because now I dropped this constraint and I add a new one, what's going to happen in the solve statement is that the same variable and the objective function is going to be preserved, but this one is not going to be because we dropped it. Okay, and then now we are defining a new constraint, and when I solve, basically what's going to happen is the same decision variables are going to be valid, same objective function is going to be valid, but this time this constraint is not going to be included anymore because we dropped it, but it is going to include this new one. Okay, and then we are going to again solve and print. Let's do this to see how the output is going to be so that you guys have a good idea about. Okay. Okay, so first I'll always check the log first because sometimes there are errors. And like sometimes I may not remember the right syntax, so I always look at the log. So what happens is like basically the problem is solved, the objective function is here, then the second problem starts, right? And then the objective function is here. Okay, let's make sure that our problem is still defined the correct way. Okay, and for that actually I'll look at the problem summaries. So let's go actually the first round. Okay, in the first problem, right, we have profit as our objective function. There are 2 decision variables, desks and chairs. And then we have 1 less than equal to constraint here. Okay. And then it's solved basically. And then the solution is like desks 500 and chairs 0. Okay. And then second time round, objective function is still profit because we didn't drop it, right? So it still accepts that. Number of variables still same because we didn't drop anything, so decision variables are same. We have again 1 less than equal to. As you guys see, although we defined 2 constraints, right? Because we dropped one of them, it only accepts the last one basically here. And then once we do that, actually the profit changed. So instead of 200,000, now it is 100,000. Okay, and then the desk actually is like halved as well. So what we can do, we can continue actually solving this multiple times. And I'm going to kind of, instead of increasing by 100, and you are supposed to increase by 100 in your homework, but what I'm going to do is like increase by 1,000 so that we can see the drastic change. Okay. Okay, so basically, actually, I don't need to have the second one because the original problem, the initial problem, okay, the initial problem, as you guys see, is 2,000. Okay, so in the first, basically, I defined this, I dropped that, I define a new constraint, I solved it, now I'm going to drop it. Now this time around, I'm going to define another constraint, and I solve it. So each of this has only one constraint, right, because the other ones are dropped. But still, it uses the same decision variable and the objective functions. Okay, and then let's solve this. Actually, what I'm going to do, since we solve, anyway, it doesn't matter. Because we can always solve one only, but let's solve all. That's fine. Okay, so what happens is basically, because we know desks are more profitable to manufacture, right? It's always like additional wood we give, it's always producing more desks. So basically 750 desks, 250, and 500. Okay. So what it does basically, as we increase, right, the only thing it does is like chairs still stays the same, 0, right? And then anything that we put as resource goes to desks immediately. Okay. So this is kind of the first part. And I'm going to kind of leave the second part to you. But we can kind of talk about it. So in the second part, it's asking, based on your findings, how much would the company be willing to pay for each extra unit of wood over its current 2,000 units? This is the shadow price, right? So basic shadow price is the increase in objective function if you increase the right-hand side by 1. So if you print the shadow price, that will tell you basically. And I don't know whether you guys remember, and I'm going to kind of comment the rest out because this is not the original problem. But the way to look at the shadow price is by dual. That's another name for the shadow price. You can either call it dual or the shadow price. SAS calls it dual. So if you just print basically the dual, it's going to tell you, sorry, dual is for the constraint. Reduce cost is for the objective function. So basically, if you print the dual for the constraint, then it will tell you the additional increment of the objective function if you increase the right-hand side of a binding constraint by 1. Okay. And then the same thing, how much profit would the company lose? It is symmetric actually. You know, the shadow price of a constraint or a dual, whether you increase or decrease 1 unit, the implication on the objective function is the same. So basically, first part of the question is going to be, if you increase by 1, then the objective function is going to increase by the amount of shadow price. And then the second one is, if you decrease the right-hand side by 1, then the objective function is going to decrease in the amount of shadow price. Okay, so this is kind of this kind of concludes the second question. Any questions about this? Cool. So this basically, for your homework, you need to kind of submit your either Excel file or a SAS file that shows how you solved it, and a small explanation for these questions. Especially like for example here it's saying you solve it to maximize. For this one, please put what's the objective function value at the optimal solution, and then what are the amounts for each of these decision variables. Okay, and this one, it basically asks you a certain question. Have a concise explanation of the answers. Basically, you don't need to kind of explain too much, but just very, like maybe for this one, for example, a table would be enough, saying that as can be seen as right-hand side increases, this is the change in the objective function. And then the second one, you can say use shadow price to explain a shadow price to answer this question, and +1 means plus shadow price, -1 means minus shadow price for objective function when we change the constraint, right-hand side of the constraint. So this kind of, I mean, last time we did the first question, now we did the second question, and the third question is going to be very similar, basically, to this ones. Cool. Okay. So this is the okay. So this is the homework, and homework is due October 2nd. Just a reminder. So today, basically, we will go through a little bit on the sensitivity analysis. I want to kind of touch base with you guys on the allowable increase and decrease concepts, because some of the questions to answer whether, you know, like how much more can we increase the right-hand side and still keep the same optimal solution, that can be answered with the allowable increase and decrease. Instead of solving the problem again, actually, you can just look at those range. So we will talk about that. And then we will talk about actually some real life applications. And these are the 4 different types of problems we are going to look into. And when we do that, actually, I think the Excel is going to be very similar. But SAS, I'm going to introduce some new concepts in SAS that you can use to model the problems. And as part of this, actually, in the employee scheduling problem, we will talk about the integer optimization. So at this point, we always assume that each of these decision variables can take any value, right? It can take the value of 2 or 2.2 or 5.2 or 10, you know, like integer, non-integer, didn't matter. But some of these questions that you want to solve in real life may require integer. Like employee scheduling is like whether a person should work on a certain day or not, right? Then that's actually a 1-0 decision. And we need to define integer variables for that. And then, as I mentioned, as we go through these examples, we will talk about reading data from a data set. Because especially for your projects, if you have like too many decision variables or big data that it's hard to model in Excel, then you may want to use SAS by read the data from a data set. And then as part of it, we will also talk about the sets. Sets makes it very easy actually to model the problems. So these are kind of 4 different things that we will go through. Okay. As you guys remember, we talked about reduced price and shadow price before. Reduced cost and shadow price before. Just to repeat, reduced cost is the increase in the objective function if you change the value from a 0 to a non-zero by 1 unit. Like basically, in this case, let's kind of interpret this one. For the X basic, and this is actually coming from a problem that we solved in lecture 4. So it was about a product mix when you have 2 products, X basics and XP. When we solved this problem, the output was reduced cost for X basic is 0. And because, you know, the reduced cost concept only applies when a decision variable is at 0, it basically tells us if we move the 0 to 1, what is going to be the increase or decrease in the objective function. And because these 2 decision variables already at, you know, at a positive number, right? Because the final values are given here, 560 and 1200. There is no concept of making them from 0 to 1. So because of this, reduced cost is 0. Okay. But if it wasn't, then you would see actually some positive numbers. Like if X basic was 0, then reduced cost would be a non-zero number. Like shadow price was, and I find actually shadow price super helpful because most of the time, right, the companies try to answer the question of whether to invest more in certain resources. Like in the case of that desks and chairs, like should we increase, you know, like what would it cost to increase the woods by 1 unit? Because that's going to increase the objective function so much or the profit so much. So reduced cost kind of tells us, and there is a concept of binding and non-binding constraints, and we talked about this in the previous lecture, but I'm just recapping. So binding constraints are the ones that are tight. Tight means that they're at their bounds. And here, maybe we can identify some of them. So here, these are the constraints. Okay, the second table here is the constraints. And you can see that constraints, the final value is actually the left-hand side of the constraint. Okay, and then here, this is right-hand side of the constraint. And it can be seen here that the second and the third row shows actually binding constraints because the left-hand side equal to right-hand side, so they are tight, okay? So for the constraints that are not tight, shadow price is 0 because basically if you increase the constraint right-hand side to 601, this is not gonna change still. Nothing is gonna change because this constraint is not fully utilized yet, okay? So shadow price basically becomes 0 for the constraints that are not tight, that are not at their bounds. And for the constraints that are at their bounds, then there is a concept of better, like investing more in it. So you see a shadow price of positive number here. And then of course, then you guys have seen these last two columns here, and this is an output from Excel, and there's a allowable increase and decrease. This basically tells us what is the range of change. What is the range of change? What range of change is okay, such that everything kept the same, like basically reduced cost or shadow prices. For them to be valid, you need to stay in a certain range. And let's go through the first row. So basically what it says here, that the X basic allowable increase for its coefficient, objective coefficient is 27.5, and allowable decrease is 80. So which means that actually this objective coefficient can decrease by 80 and become 0, that's fine. Or increase to 107.5, and that's fine too. So between that range, basically, this reduced cost and everything is going to be still safe. So this is basic. This tells you basically what is the range such that the decision variables that are non-zero still going to be non-zero, and decision variables that are zero are going to be still zero. The binding constraints that are binding are going to still binding, and the constraints that are not binding are still not going to be binding. Basically, it tells you the almost like the tolerance around your optimization function. Okay, and this would be, so basically you have two alternative ways. Either you can utilize this table for some of the questions, or you can actually, for example, with SAS, you can solve the problem multiple times and then find what the range is, such that the decision variables that are zero still zero, decision variables that are non-zero still non-zero. Okay. So this is kind of the way to deal with it. I mean, in my experience, usually to be safe, it's always good to rerun these things. And and you will see that actually when it comes to the problems with the integer program, integer variables like employee scheduling, you cannot do this anymore. So this is a very special case of basically having this information ready is a very special case of linear programming problems. Okay. Any questions about this? Okay, so I kind of, what I said actually is explained here. And again, as I mentioned, in SAS, there is not an easy way to do this, except that you can run the problem again and again. And basically, you can change the right-hand side and see whether the solution is changing, change the right-hand side again, see the solution changing. You can do this kind of iteratively. Okay. So this kind of actually concludes chapter 13. And now we will start talking about chapter 14. And chapter 14 actually is probably the chapter that you will start seeing all these examples of how these tools are going to be used. And here specifically we are talking about the optimization tool. Because now I know that we talked about the theory and we talked about simple problems, but there are many, many, many actual practical applications of these problems. And many companies actually uses them, like in my experience, like the Amazon, FedEx, all of those big logistics companies, they are definitely utilizing optimization a lot. Same as Walmart and those companies. Usually when there's a big scale, as well as the airline companies, like price optimization is a big thing, for example, for airline companies, or even the scheduling, because there are so many planes coming and going. They need to make sure that they give the right spots to right planes. So there are so many applications, especially in the for big businesses, these tools. And then also another thing is like the investment banking, like coming up with the right portfolio. They use the optimization tool to get that.
So, Dr. C, a question there. So you mentioned there's no easy way to get this in SAS. Is there an easy way in Excel or any other tools for sensitivity?
Definitely. And let me show you actually, maybe I wasn't clear. You can see actually in Excel, this is an output from Excel. And Excel gives you this. And let me actually, I'm just going to open and show you how you can produce this with Excel. And you guys actually have this. This is uploaded. Okay, under module 2, you can see this case. So I'm going to kind of create it from the beginning, okay, so that you know. So this is the optimization problem we defined basically in lecture 4. Okay, this is the beginning of chapter 13, Introduction to Optimization. And just to remind you, the question was maximizing the profit. And you have a bunch of constraints, basically. And the idea was like coming up with the right mix of products. Okay, and here right mix of products are like how many from X basic and how many from XXB to manufacture. Okay, so when we have this problem, you know, under data, you have the solver, right? And we define this problem, like we define the objective function, we define the decision variables, we define all the constraints, right? And then we hit the solve button. Hold on, what is the objective function here? Okay, let's fix this. I think objective function needs to be yes. So I'm gonna just, this was the objective function. Okay, let's then check the rest of it. Okay, this is the decision variable, correct? And then F10, H10, F11. So okay, this looks correct to me. So I'm gonna hit the solve. Okay, once I do that, it pops up, this window pops up. And then there you will actually pick the sensitivity here. And you can, if you want, you can check the answer as well. See, this is like a multi, you can pick multiple things here. And then once you hit the OK, now it is creating new reports. I mean, because I ran this before, right? It created now the second one. And here sensitivity report basically tells you what is the range of changes is okay. And you can keep the same, zero and non-zero variables. So here, for example, kind of, let's go through this one more time. Okay, so let's, for example, look at this row. And then let's explain kind of what it says. So here what it says, and focus on these two columns, by the way, okay? We are going to talk about them. So it says basically, if we increase the objective function coefficient by 27.5, so basically if we make them 107.5, or if we decrease by 80, which means that we make it 0. So this range from 0 to 107.5, the decision variable X basic is still going to be a positive number. Okay? It may not be exactly 560, but it's going to be still positive. So this basically, these two columns tells you what is the tolerance such that you can still keep the same decision variables positive, same decision variables 0, and then same constraints binding and non-binding, of course, you know, like depending on, right? And let me demonstrate you. Okay, so basically we solve this problem, right? So what it tells me here that if I decrease the objective coefficient here 80, if I make it 50, it's telling me I should have a very similar optimal solution. And let's kind of change it and let's solve the problem. So instead of having 80, let's change it to 50, because according to sensitivity report, I can do this, right? Because sensitivity report tell me that I can increase up to 27.5 and I can decrease by 80. Okay, this is what they, you know, this is how you interpret this. So basically 50 is within this range, which is like decreasing by 30, right? Because original was 80. And let's solve this problem again, right? I can actually, and see whether what the sensitivity report says is correct or not. Okay, this time let's make sure that, okay, this is the objective function. We change the coefficient to from 80 to 50, and let's solve again. Okay, I'm gonna hit this too so that we can compare it to. Okay. So what, you know, like, did you see what happened here? Like, although we decrease this to 50, we still have the same exact optimal solution. So just to recap, we solved our problem, original problem, right? And we got this sensitivity report. And according to this sensitivity report, it basically told us it's okay to decrease this objective coefficient by 80 and then increase up to 27.5. And if we do that, our objective function and the optimal solution is going to be still same. right? And then what we did is like we said, okay, let's try whether it is correct. So then I said, okay, instead of having 80, let's make it 50, because 50 is still within this range. And then I solve the problem again, right? And then once we solve the problem, here, this is the report from that, it still tells me exactly the same solution. So basically the point here is like there is a tolerance around these coefficients. And then the nice thing about linear programming, actually, there's a formula that can be applied to get these allowable ranges easily. And Excel has this. Like, let's kind of do the same thing here on the constraints. Okay, so this is it clear? How do you interpret this for the objective function?
Yeah, I think so.
Okay, so let's do that for the constraints as well. So here we need to kind of look at two things: binding and non-binding. So basically, you guys can see, right? This is, I'm going to kind of make them red. This is binding, not red, but orange. This is binding, right? And then this is binding, okay? And the white ones are non-binding. So here, what you see here actually, because this is non-binding, right? If you decrease the right-hand side 600 to 560, which is by 40, you still keep the same optimal solution, which makes sense, right? Because this was already 560. Left-hand side is 560. So if you decrease 600 by 40, which is said here, it's fine. Nothing is going to happen because we already not utilizing everything about this constraint. This is how you get actually the allowable decrease. Like the slack basically becomes your allowable decrease for non-binding. Okay, and then the allowable increase here, this actually means infinity. This is the biggest number that Excel can handle. So this is why it is like that. But this is basically infinity. So which means that you can increase actually the right-hand side as much as you want. Nothing is going to change. And which again makes sense, right? Because this constraint is not binding, which means that it's not that necessary. Like we are not utilizing the full thing, which means that if you make this 600 to 601 or 700 or 1,000 or 10,000, 1 million, doesn't matter. It's going to only use 560. Okay, so basically here, this is how you interpret allowable increase and decrease. So this basically says that if this 600 drops up to 560, it's fine, nothing is going to change. Or if this increase to infinity, again, nothing is going to change. Okay, let's kind of do the same thing for here. So this one actually is a little different, right? It is actually, because this is non-binding, this is binding, it is not so easy to get what the numbers here are. So this basically says that allowable increase is 50 and the allowable decrease is like 33.3, which means that our range becomes either you can decrease by this much or you can increase by this much. Okay, so this is the range that you can kind of fluctuate. And if you do that, still you can keep the same solution. Okay, same solution. Actually, this is going to be a little different. Same solution here is going to be binding constants are going to stay binding, and positive decision variables are going to stay positive, and 0 ones are going to stay 0, but the values may change. And let's try this actually. So basically here, what it says is like this one can change up to 1250 and down to this number, right? So what I'm going to change it to is like maybe 1190. Okay, so I'm going to the problem definition. I'm going to update this so that this is original. And then instead of having 1200, okay, I'm going to change the right-hand side so that it is like 1190. Because according to the allowable range, right, it tells me that I can fluctuate here and I should keep the same solution. So then if I solve this problem again, and you don't need to solve it, by the way, I'm just demonstrating what that means. You can just use that coefficients directly. And if you solve this, okay. So what happened actually here, and I'm not gonna repeat, like keep things, but what happened here actually, you can see that although we had a different right-hand side, we still have the same solution. Okay, so basically what it told us here is correct, right? Because we change things according to the allowable increases and decreases, without getting out of that, and then we have the same solution. So this is the concept of sensitivity. Basically, you are just looking at to see, the sensitivity of your solution. So if you don't have the right parameter estimate, like for example, we have these numbers, right, the right-hand side. Let's say that somehow someone made a mistake. They didn't input the right number. This range tells you how sensitive your solution is. Or another application we talked about, like if you decide to invest more and then increase this right-hand sides, then you know that actually if you increase the right-hand side, like up to 1250, nothing is going to change. So if you want to increase it, you need to really go maybe 1260 or something, right? You need to get out of this range, because as long as you stay within this range, nothing is going to change. So when you are basically increasing your right-hand side, right, you need to get out of the range.
So Dr. Z, functionally, we are saying that if we are making 1167 basic and 1250 XP, we are going to make, our profit will continue to be the same. We have our optimized function. That's what it means, right?
Can you repeat again?
No, I was saying that between that range, our basic and the XP model, if we make, our objective function will continue to be the same. That is what functionally it is saying.
Yes, that's right. So this is kind of how you do it. So try and see yourself as well. Like basically, whenever you see the range here, try to change the problem and see whether it holds. I think that kind of will make you understand the meaning of these things better. And another alternative is, I think I'm actually fine with that too. Like you can solve the problem again. That's fine too. And see whether things are changing. So that's another, like two ways kind of to go after this problem, depending on what you prefer. Okay. Cool. Any other questions on the sensitivity and? Okay, so I'm going to kind of jump into employee scheduling problem. Okay, so now actually for the rest of this lecture, we will talk about a couple applications. Basically, the first one is going to be about scheduling. Then we will talk about an example of a product mix. And then the last one is going to be on the transportation. Transportation one actually is going to be about network optimization. And I actually worked on a similar one, but this is going to be a little bit of a simplified form. A very similar concept actually is being used in Amazon retail when they are deciding from which warehouse to ship to which customer region. So actually, they basically solve a big LP problem, and then this optimize constantly depending on the current levels of inventory and the demand forecast. So I think these three things, basically the product mix, employee scheduling, and transportation, is going to kind of cover a good amount of industry example. Of course, these are going to be always a little bit simpler because we don't want to kind of spend the whole lecture on a small part of things. But the general idea is going to be same. Once you get the once you get the idea of how to model stuff, then you will be able to deal with the more complex constraints and objective function. Okay, so this problem basically is developing an employee schedule for 7 days of the week. But there is one constraint, which is like if someone starts working on a day, they will continue working for the full 5 days. Okay, so if someone starts working on Monday, basically, then they need to work at least 5 days: Monday, Tuesday, Wednesday, Thursday, Friday. Okay. So that's the constraint. And then at the end, we want to minimize the number of employees we need. But also, like we have a requirement that every day actually we need at least minimum number of employees. So for example, it's given here. Monday, we need like 17 people at least or more. Tuesday, 13. Wednesday, 15. Thursday, 19. Friday, 14. Saturday, 16. And Sunday, 11. Okay, so these are kind of different, different requirements. So basically, the objective function minimizing number of employees. Constraints are if someone starts working on a day, they will continue working 5 days. And another constraint is that we need to fulfill at least this many people for each day, because maybe some work is coming and they know that they have minimum that many. So what we will do for this, actually, I will open Excel and we will go through Excel first, and then we will do the same thing with SAS and see kind of how it can be implemented in both. Okay. Let me actually make it a little bigger. Okay, so here I of course I worked on it, like before I showed you guys, but I'm gonna kind of walk you through step by step. Here, this is the color coding I use. So the blue ones, and I'm gonna kind of actually remove that. Okay, so the blue one is what the solver is gonna determine. So blue one is our decision variables basically. Okay, the orange ones are the expressions that I wrote, and then the green ones are given to us. Okay, so and then yeah, so objective function is basically, I think the easiest among these things is summation of all the employees who are going to start on each of these days. Okay, so here the decision variable basic number of employees who are going to start on that day, and then once they start on that day, including that day, they will be available for 5 days. So for this one, basically, objective function is going to be summation of these 7 rows, right? I think the complicated part here is this part. So as you guys remember, one of the constraints is like whenever someone starts, they will be available for 5 days. So the way that we did that is like basically, I define Monday, like here, this tells me how many people are going to be available. Sorry, how many people are starting. Okay, and then this is the how many people are going to be available. So basically, if someone starts on Monday, right, they will be available on Tuesday, and you guys can see the formula. Just pay attention to here. This is B4, and this is B4 too. This is B4 too. So basically, once they start, like once the solver determines, all of these are going to have the same number. Basically, this is Monday's, this row that I highlight, Monday's contribution to each of these 5 days. So you can basically say that this cells tells us the contribution. Okay, so those are the contribution of each day on the other day. So here, this row tells us the contribution of Monday, people starting on Monday on different days. And then the second row that I highlight tells us the contribution of the people starting on Tuesday to other days. Okay, at the end, Monday, we are going to have people who start on Monday. People who started on Thursday actually are going to contribute to Monday. People who started Friday are going to contribute to Monday, because people who start Friday needs to work 5 days, right? So it becomes Friday, Saturday, Sunday, Monday, and Tuesday. So as you guys can see, people starting Friday are going to be available on Monday. Okay, and then the same thing for Saturday, and the same thing for Sunday. Okay, so basically this matrix tells us who's going to be available. And here, basically what I did is just, B4, here, these are all B4s. These are all B5s, right? And these are all B6. So it kind of goes like that. And then at the end, people available on Monday are going to be a summation of this. And it goes here, basically. Okay. And each of them are going to basically same thing. These are the Thursday available people. These are Friday. Because each day basically is not just the people starting on that day, but the people started in the previous 5 days are going to contribute on that day as well. So then basically this is it. Like once you determine this, it's just a matter of kicking this over here. Oh, let's get back. Okay, we missed solver window. Okay, let me just close this. I think because this is full window, it just cannot pop up that solver. So I'm going to just make it small and then kick this over again. Okay. So basically each of this, I define the same as before, objective function. We want to minimize number of employees, and this is the decision variables, and these are the constraints. Okay. And so one thing that, so this is the time that we are going to actually introduce the integer variables. So you guys can see here actually we define a new constraint which is like integer, and I want to kind of show you what it looks like. So basically you take the cell, and here in this case it is like B10, and then you here in the drop down there's an int. You pick the int, and it automatically populates this one integer, and then just edit basically. So here, this is a point, right? In the linear programming, each of these decision variables can take any value, right? They can take 1 or 1.5 or 2, 2.3, you know, like, but when it comes to the employee schedules, we cannot ask half of a person to start on a day. So it needs to be an integer. So it needs to be either one person or two people. So because of this, we need to enforce this integer on the modeling, okay? And this is the way to do it. And one thing I'm going to mention actually, when you do this, it's still not going to do it because there's an option here that you need to check. In the option, there's actually a checkbox which says ignore integer constraints. And in the default is unfortunately is checked here like this. So you need to uncheck so that Excel respects the integer constraints. Again, I want to repeat this because this is a point that will prevent you from solving the integer programming problems. So basically, integer programming problems are the problems that the decision variables, at least some of them, are supposed to get like integer numbers. And we said that in employee scheduling, this is the case because we cannot ask half of a person to start on a day, right? It needs to be a full person, 1 or 2 or 3 or 4, right? And then because of that, we need to enforce integer. But then once you enforce and solve, actually Excel is still not going to make this decision variables integer, because it seems like there's an option under here, and when you click, you will see that there's a setting here, and the default for this setting is checked, which means that although you say integer in the earlier model, it's going to ignore. And I'm not sure why they have this option, but you need to uncheck this one and then hit an OK, and then solve it. And then once you do that, it populates basically all the decision variables. Okay, and then as you guys remember, I mentioned to you before, like sensitivity analysis is an available tool for linear programming problems, but it is not an available tool for integer programming problems. So in the integer programming problems, if you want to change the right-hand side, then you need to change and run the problem again. Because the linear programming problems have a nice mathematical form, and that gives you that formula immediately. But the integer programming problems are different, they are discrete, right? Because of that, sensitivity analysis is not something that the mathematical models can produce immediately. And because of this, if you want to change right-hand side or the objective function coefficient, you need to just change and run, basically, okay? And then I'm going to say okay here. So this is how you basically solve an employee scheduling problem in Excel. And at the same time, also how to make sure that your problem runs as an integer problem rather than a linear problem. Any questions on this? Okay, so I'm going to jump to SAS. Okay, and all of these files are uploaded under module 2. So if you guys want to later run it and like kind of try yourself, you can find them actually. They're under module 2. So there's actually the lecture notes. Let me actually show you. Okay. So under module 2, so this was the first 2 lectures on optimization, right? And this is the lecture that now we are talking about. And all the files that we use are here, like the SAS files or the Excel, everything is here. So you can download them and then try yourselves as well. Okay, so now I'm going to open. This is not the right place. So I use N drive to store all of the stuff because N drive basically doesn't disappear, but the desktop itself disappears, right? Because this is a remote desktop, so that's a virtual environment. So if you guys want to kind of work on the remote desktop, use the N drive. Okay. Now let's go through this one. And the nice thing actually in the lecture notes, what I did is I point out actually different things, like what they mean, like I label them. So if you have hard time later when you are listening to the lecture, you can also look at the deck to understand what each of these components are. Okay, let's go through. As I mentioned before, we are going to use Prokop model, right? And we will invoke Prokop model with this statement with a semicolon. So one new concept that I'm going to introduce is the sets. Okay, sets are like indices basically, and it's super helpful because you can define decision variables or the constraints or the numbers over sets. So here, the set that I'm defining is days basically. So for each set element, I'm going to use a string. A bunch of characters basically indicates which day of the week it is. Okay, and I'll show you how it is used here. So basically here we are defining a decision variable which is X, and here X actually is the number of employees here who is going to start on the corresponding day. Okay, and as you can see, I use days when I define the decision variable. Okay, so what this does is, so I can actually, an alternative to this is this, right? I can actually say X Monday, X Tuesday, X Wednesday. So I can actually define each of the decision variables like this. But then I need to define 7 of them, right? And I need to say this is greater than 0, and it needs to be integer. And then the same thing applies to each of this. And then we need to repeat this again, right? Because we need the Thursday, we need the Friday. So basically, we need each of a decision variable for each day, right? But instead, actually, what I can do is like, I can define a set, and then I can define X. Inside curly brackets, it says days. Okay, and then we can just one time can say greater than or equal to 0 and integer. And then this is going to be applied to all of the decision variables there. Okay, so this is a nice thing about sets, and we will actually see uses of sets for other things as well, like the constraints, or like in the second line, in the third line, actually, you are going to see how to use it in the numbers too. So for example, we define a number because number is a parameter that's an input to the model. And here, basically, we are saying that the required employees defined over days. And we define like 7 numbers. And I'm going to kind of show how it was in Excel so that you guys can kind of, picture it better. As you guys remember, one input given to us was the employees needed each day, the minimum number of employees needed. So it was like 17 for Monday, 13 for Tuesday, 15 for Wednesday, 19 for Thursday. And you guys can see the numbers here, like 17, 13, 15, 19, like that, right? So this is actually, but then one way to define this again, one by one, we can say required employees for Monday, required employees for Tuesday. Like, actually, let me write it. So basically, I can do this, right? I can say none. Required employees Monday equal to 17. Required employees Tuesday, it is 13. So basically, I need to define 7 of this. Like here, this 2 line, I need to repeat it 5 more times, but this time for different days, like Wednesday, Thursday, Friday. But instead, actually, we can define only 1 line, right? But this parameter is going to be defined over days. And each day basically is going to have a right-hand side, right? Defined here. Like you basically put a square bracket and then separate by comma. This is again a number basically. Okay. And then after that, we are going to define basically a constraint for each day. So you can see that constraint for Monday is here, constraint for Tuesday is here, and all of them are here. So basically, Monday constraint is going to be, I want to kind of remind you again what we are trying to solve here. when an employee starts on a day, they will continue working 5 days. So if an employee starts on Thursday, then they're going to work on Thursday, Friday, Saturday, Sunday, and Monday. Because of this, people starting work on Thursday are going to be available for Monday. People start working on Friday, again, they are going to work on Friday, Saturday, Sunday, Monday, and Tuesday, so they are going to be available for Monday. So each of these days, basically, people starting are going to be available for Monday, including the people starting on Monday, right? So then this summation here for different days is the total number of people who are going to be available on Monday. And they need to be at least this many, which is the required number of employees for Monday. And if you look up, it is 17, right? The first number here is 17. So then we define the same constraint basically like 7 times here. But the days are different, right? Because for Tuesday, people starting on Thursday are not going to be available anymore because they're going to stop working. Because Thursday, people work on Thursday, Friday, Saturday, Sunday, and Monday. Monday is their last day. So as you can see, when we define the left-hand side of this constraint here, we don't use Thursday anymore because Thursday, people starting on Thursday, they finished working end of Monday. And then same thing for Wednesday, like people starting on Friday are going to work on Friday, Saturday, Sunday, Monday, and Tuesday, but they're not going to work on Wednesday anymore because they finished their 5-day shift, right? So because of this, when we look at Wednesday, you don't see the Friday contributing to the left-hand side of the constraint. Okay, so basically it goes like that. Like for each day, we need to figure out which people starting on other days, which one are going to be still available, and then sum them. And then they need to be greater than the input variable given to us. After that, basically, this is all the constraint. Then we will define the objective function. As you guys remember, objective function was summation of all the employees. I'm going to show you an alternative way. So this is the compact form, right? You can actually sum inside the index and basically then say that I want to sum over this x variable. Okay, or you can say this min total employees. Basically, they are this, right? X people starting on Monday, people starting on Tuesday, people starting on Wednesday, people starting on Thursday, right? People starting on Friday, people starting on Saturday, and people starting on Sunday. Okay, so basically this line is same as the second line, but it's just a compact form. Okay, so it's just shorter. It's like the summation. It says basically sum over all the indices of the days set over x. So as you guys can see, this is a little more complicated. So what I would recommend, just open this and then, kind of going line by line and see, like whether you get what you get, whether you understand whether what it says or not. But I think here, the main topic of this example is showing you the sets and indices. Okay, and how to use them kind of so that you don't need to write everything in explicitly, but you can just put a compact formula as shown here. And then once we solve this problem, we will see kind of what the solution is. Okay, so I'm cleaning the log. This is actually something I do because log gets very crowded. So if you hit the log and then hit this, it will clean it up. Okay, so it makes it kind of nothing left, right? So then I again hit back to the editor window, like here, put my cursor here, and then I'm gonna hit this submit. Okay, first let's check the log to make sure everything is good. Okay, so according to log, everything looks good, but this time it's actually using a different solver, which is called MILP. MILP is an integer programming solver, and then the objective function is 23. And this is each day how many people needs to start. And the reason we got this one because we have a print x statement at the end. This one. Okay. So this is the employee scheduling problem. To recap, right? This is the first integer programming problem we solved. We solved both in SAS and Excel. In Excel, there is I don't think there is anything new except we add the integer constraints in the solver. So if I hit the solver, you see some integer constraints here. And the way to get them is like regular, right? You just, you just basically hit the solver, you say you want to add a constraint, and then you basically pick the cell. I want this cell, I want it to be integer, and then I want to say, okay. Okay, this is what you do. And then you just solve it. But while you are solving it, this is one trick that I showed you. Like this is not going to still solve integer unless you uncheck this option under options, which is ignore integer constraints. And once you do and hit the OK, it's going to solve it as an integer problem. Okay, so basically in this basic lecture, you learn how to do and how to add an integer decision variable to an optimization problem. When it comes to SAS, you learn the integer, right? Because we put an integer phrase here. But at the same time, you also learned about the indices and sets. So instead of writing the constraints or the objective function explicitly, one way is writing it with the index sets. And here, index set is defined like this. So in this case, because each day is an index for many of the things like decision variable or objective function, we define days like this. And I use them to define the decision variable here, and then the objective function. The only difference is basically inside the curly brackets, you are putting days here. So then what it does is like it is defining like 7 different decision variables. For each index of this set, it's defining a decision variable. Okay, and then basically you solve this problem. So this is the first concept. Any questions on this? Okay. So the next one that I want to jump into is a product mix problem. So this is actually this is not from the book but this is a very common use case in industry. Like basically up to this point, right? All of our problems have very few parameters. Basically, it has like maybe 10 numbers that we need to input to our model. Like the numbers that I put here, like this green, you can see that we only have one green, only how many numbers here? Like 7 numbers, right? But you will see that actually in real life, the examples that I gave you, like like the plane scheduling or the transportation optimization for FedEx or Amazon, they actually have lots of input. And no one is going to kind of enter them by hand, one by one, right? Because that's going to be too expensive. And then if you need to change something, it's going to be very difficult. Like if you think about demand forecast, that's something that changes every week or maybe every day even, right? For some products. So in that case, your inputs to the optimization problem changes, which means that actually instead of using like writing them up like one by one, you may want to input them from a file. And this is a very useful skill to have, and maybe for some of your projects this is going to be very relevant. Okay, so in this example, basically I'll show you how to use files as an input to the optimization problem and solve them. So in this problem, basically we have 100 different products, and each product has a profit, and they have a cost. They also have how much space they consume. Like basically, they need to be stored in some place, and we have an idea how much space they are going to occupy. And then also they have demand corresponding, right? So you can see that each row basically is a product, like there's a product index, and then the first column is the profit. Column B is the profit, column C is the cost, column D is the space occupied, and then column E is the demand. And what happens is, like, basically in this question, they're asking us to maximize the profit, right? By buying some of these products and storing them in the store. But while they do, there's a budget constraint. So you cannot buy a lot of things, right? There's a constraint that you have on the budget. And then there's also a space constraint. Like, basically there's a limited space that you can store these items, and it cannot be above certain limit. At the same time, the maximum demand is forecasted and given to you. So basically here 34 means that you will never have more than 34 units of demand, which means that you better not buy more than 34 units. So it's going to be kind of less than equal to constraint. You can see, like, I have like 100 rows, and this is a simple problem, right? If you think about Amazon's case, they have like millions, 100 millions of products. So basically being able to input them will be very helpful. So in this one, basically, I'll kind of open another example. And again, this is uploaded under module 2, so you guys can have a look at it. So the name of this problem is larger scale optimization. Okay. So this is the problem, and I will go through one by one. Okay, but one thing we need to first do is, like, you can see that it uses data, and this data hasn't been imported. So first I'm going to import this data so that it's available for SAS to use. Okay, so we did this actually for homework 1, right? So file, basically, I will go to import, and the file that I have is Excel, but sometimes people have like CSVs or TXT, you know, like depending on what you have. And then I'm going to browse. I think it's on lecture 5. Let's see. Oh, sorry, maybe lecture 4. Okay, so the format of the file is the latest one. So this is the Excel file that we want to import. So basically we picked it, and then I'm going to say okay. And then if it has multiple tabs or sheets, then you can actually select them. But in our case, there's only one. So there's 2, but we are going to pick the one. And then we need to name it. So what I want to do actually, I want to make sure that I copy it right, but I need this name. Because in my code, I use this name. So then when I'm importing, I need to use the same name. So I'm going to import. Okay, we are going to start from the beginning a little bit. So the name needs to be large scale product mix. Of course, other alternatives, like I can give a different name and then change the name in the code. That's fine too. Large scale product mix. Okay, so let's finish. Okay, now this data, let's check the log. It seems like, okay, it is imported. It has 100 observation, which means 100 rows, and it has 5 variables. Okay, and let's look to see how it is, like whether it's done properly, because sometimes it's imported, but there's a format problem or some other problem. So again, what I did is here, I hit the Explorer. Okay, under Explorer, there are libraries. So data sets are kept in libraries. Libraries are like, you know, drawers, basically, or folders, right? And then under, we have multiple libraries. These are default ones. You don't need to worry about them. But the one that we keep is the work, which is the temporary library. And temporary library, basically, in that session, everything is going to be available unless you delete them. But once you close the SAS session, they're going to disappear. There are ways to do permanent libraries as well, but it is out of scope for this course. But feel free to kind of check it out. It's very common, like having a permanent library and then storing things there so that next time you come, you don't need to import again. Okay, so this is the file we imported. It has 5 columns, and it is very similar to the Excel file, right? But the good thing is now Excel file wasn't directly available to SAS, but this file is. So we can read from this file, basically. Okay. So in this optimization problem, what we are going to do, we are going to utilize multiple things again. We will utilize sets. Okay. And then we will utilize reading data. Okay. You can see here, I have, except the maximum space and maximum budget, and then the number of products we have. I haven't defined anything else, right? Everything is basically are going to be read from this data. So these are numbers. Numbers, basically maximum space is a number, maximum budget is a number, right? And then number of products, we are inputting it. And then product set is defined as a index set. So when I do 1.n, what it's going to do is like 1, 2, 3, 4, 5 until n, and here n is 100. So alternative is like I can do like this. Okay, 1 to 100. And we can keep it like that. So then basically this index set is going to be available for everything that we are going to do, right? Because each product has a profit. So then we are going to define this profit for this index set. So then it means that each of the items for each of this index is going to have a profit number. Then the same thing for cost. Basically, product index is going to be from 1 to 100, right? This is a number from 1 to 100. And one alternative way, actually, instead of product index, I can always use this, right? It's going to be fine. It's the same thing, basically. Either you can define the product index once and then use it everywhere, or you can write this everywhere. Okay, so the profit, cost, space, demand, basically all of this are going to be defined over the index set. And then we are going to read from the data set that we create into these numbers. And this is pretty simple. Read data, this is part of the syntax. The blue things are part of the syntax, okay? So read data. Then you are going to put the name of the data set you have, which is the one that we just imported. And then we will put into. Again, this is default, so you don't need to worry about it, just write it. And then you just write the column names, which are same as the parameter names, profit, cost, space, and demand. And automatically, each of these are going to get the profit number, cost number, space, and demand number from the data set that we created. Okay, just to recap, so what we did so far is like we define numbers, we define a set, and each of these numbers are over this set. And when we read into these parameters, they basically got the number from this table. So what happens is profit here, this alternative ways I can write each of this, right? I can say profit 1 is this, profit 2 is this, profit 3 is this. You know, like I can kind of put it line by line, but it is not going to be like a huge code, right? Instead, I can just read this data into profit, cost, space, and demand. So what I would recommend, if you want to try it yourself, have another data, right? And then just repeat, copy paste my code, and then just change the way column names or something, and then see whether it works. That's a good way to try. Okay. So now up to this point, basically, this is all defining the parameters. Okay. Once you define the parameters, then the next three things is the decision variables, objective function, and the constraints. Okay, so basically we are going to define these three things there. So here, the decision variable, I call it buy. So this is basically telling you how many units of the item that we are going to buy. Again, to recap or to remind you, the problem we are trying to solve is determining the right mix of products so that we can maximize the profit while we are respecting the space and the budget constraint. Okay, so basically the decision variable here is like we are going to decide how many to buy from each product. And the name of the decision variable, I put buy, you can put X, it doesn't matter. Okay, okay, I'm going to actually, this is not okay. It's supposed to be like this. Okay, So then we define a decision variable over the product index. That's a set, right? So this means that actually each item in the product index set is gonna have a decision variable, a corresponding decision variable. So here basically it is var, which defines a decision variable. And then the name of the decision variable is by. And then we are going to define it over a set which is called product index. So this is the decision variable. So once we define that, the next step is defining the profit function. Okay. So we will define the profit as such. So buy tells us how many from each product we are going to buy. And then the profit tells us how much money we are going to make from each unit of each product. Here, the objective function basically is summation over the set. We multiply the number of units we are going to buy with the profit. Okay, and then this is going to give us the total profit. Okay, and then with the same thing, you know, we are going to actually repeat this part that we have. We are going to repeat again and again, but for different applications. Like here, for example, we want to understand. Oh, this is not right. We want to understand how much space, right? That each item is gonna, how much total space all of these items are gonna occupy. Then it is gonna be the, again, summing over the index set, multiplying the space with the by. And that needs to be less than maximum space. And then we will do the same thing with the cost and then the by, because each item cost and we have a budget limit. So then that needs to be less than the max budget, which is defined up here, right? And then the last but not the least, we have a demand constraint. So demand constraint, each product basically needs to be less than or equal to the demand given. And this is how we define it. So here you can see that we define this demand constraint like 100 times because we are defining over the set, right? And then we are saying that each, like when I is 1, then it is going to be by 1 less than or equal to demand 1. Okay, so basically it's going to be, this is going to populate 100 constraints, and then we are going to solve. And at the end, when you solve, of course, you will have 100 different products, right? So you may want to input them to a data set because it will be hard to see if you just print it. And actually, we can try this. Okay, so I basically put a print by. Did I put print by? And now I'm going to print. You can see, right? I mean, like it's printed here. So we know, for example, the first item we are going to buy 24. The second item we are going to buy 78. But this is so many, so we need to kind of scroll down, right? Instead, actually here, we created a data. And the data is called by data. And then we just say, basically, this is like a standard format. You need to put this I here. Like basically, create data you need to put. You need to have a data set name. And this is up to you what you want to name it. Then you have a from. And then you have an I. Again, I, don't worry about it, just put it there. Then you need to put the name of the decision variable here. So this is going to be the column name. This is going to be the decision variable. And here I put them the same. It's kind of easier like that. And once we do that, see, we have a by data, and it is here. And the nice thing is actually you can export this data to Excel. So you can say file and export data. And then you can say that I want to export by data to an Excel file. And you need to specify a location. So let's say that we want to put it under the lecture 6. So I want to have it like a regular Excel. Maybe it's like the by data. So same as import, there's an export. So you can export it to your data. And I'm going to say, OK. And then, I don't know, by data. And let's finish. Okay. So now what happens is like actually this data is exported. So if you want to use an Excel file, for example, send it to someone or input it to another system, actually there's an Excel file right now on my computer that we can have a look at. Okay. There's an Excel here. This. Okay. So you need to I need to open it from the remote desktop because this file that I exported is to the N drive, so it's going to be there. Okay, so while it is opening, I will just recap what we did here. So this is a more advanced application of optimization, right? And in this advanced application, what we did is like we inputted a big data into the optimization model. Instead of writing things one by one, we read the data. Let's browse it. And it's under N, it's under lecture 6. See, it is here. So this is the data we exported. So this is the output of the optimization model. Okay. So basically, go to read it yourself. You know, this is a little bit of an advanced example, but it is super useful, especially if in your project you are going to solve a big problem, you know, big, larger scale. So this kind of saves you time by not making you, you know, type everything. Here, basically, you're going to read the data and then use it in your optimization model, and then kind of write the data back, you know, write the optimal solution back to a table, and then you can export that table to Excel. Okay. So this is again, you know, like in this lecture, we are going to little bit advanced applications, because applications are important to understand, you know, like so that you can apply this to later, right, to businesses or in your industries. So, but by nature, usually these problems are a little bit more complicated. So basically, if you don't get it the first time around, just listen again. Maybe open the file, save it, you know, like solve it yourself, maybe change a little bit and see what type of error messages are there. I think that will be the best way to learn about this. Okay, so this is kind of the, I think, second example that we went through. So this was to determine the right product mix while maximizing profit, but making sure that we are not over the space constraint and we are not over the budget constraint. Okay. So now the next example that we will go through is going to be a network problem. Okay, so this optimization is super common in transportation when modeling transportation problems. And there are different types, you know, like there are many different types of logistic models, but the one that we will talk about is the network model. Okay, I'm kind of going, so basically in a transportation problem, usually there are capacities, right? Basically, either you have limitation on the number of trucks that you can ship, or you have limitation on the space for your warehouse. So there's always some kind of, you know, capacity-related restriction. And we need to make sure that we flow a right amount of materials, or recommend right amount of materials, so that these capacities are still they are not violated. They are still, you know, like the solution complies with it. Because if it doesn't, right, then no one is going to implement that solution, because if you are above the capacity, there's no way that the business can run that. Unless, of course, they stretch themselves, like maybe the overtime, maybe outsource some of these trucks. But then that type of thing needs to come from a sensitivity analysis. Okay, so basically, usually in transportation problems, there's like capacity constraints. And then there's always customer demand. I mean, like in most, right? There's always some demand, because we don't want to just ship items without thinking about what the customer demand is going to be in that region. Because if we do, right, then it will be kind of waste of money. We are going to ship it, it's going to stay there, no one is going to buy it. So we need to make sure that we are aware of the customer demand on those. And then last but not least, of course, it's going to cost some money. And the point of all of this is going to be kind of minimizing the cost. Like we want to minimize the cost such that we can fulfill customer demand, we respect the capacity constraints or the limitations, and then we find the solution that fits it, while, you know, like while not violating any of these things. So again, just to recap, right? We went through in this lecture, we are going through applications of optimization, And we went through two applications. One of them is the employee scheduling, and then the second one was the product mix. And this is a third example, which is transportation models. So as I said, like many times, during this lecture, this is one of the most common application of large-scale optimization, like transportation models. Many companies, like the retail companies or the UPS or FedEx, and like the airlines, like the plane scheduling, which gate is going to be assigned to which plane or the airlines, like those are all kind of optimization related problems, and they are very similar to these applications. And especially the transportation is one of the common one. And actually companies save lots of money by running optimization models for their transportation problems. So in this one, this is again a simpler version. And in this simple version, basically, there are plants and there are regions. Each region has a demand, but there's a capacity. So a plant cannot ship more than a certain amount of units, okay? And basically, we need to respect that. But at the same time, we need to try fulfill the demand in each of these regions. So here, let's kind of go through these numbers, what they mean. So for example, here, this is the plant 1 to region 1. This is the cost. So it costs basically $131 or whatever the like monetary unit per unit to flow 1 unit between region 1 and plant 1. Okay, and that basically these are the cost components, and then the capacity is given here and demand is given here. I'm not going to go through them right now, but I'll go through them as we model the problem. I think this makes it very clear. Like this network diagram for transportation problems is like super helpful to understand what's happening. So basically, there are plants. Okay, and they are usually called the plants, or the initial node in a transportation problem is called usually the origin. So basically here we have 3 origin nodes, like plant 1, plant 2, plant 3. And then we have destination. Right, we have destination nodes like region 1, region 2, region 3, region 4. Okay. So, and then the idea is like basically each of these arcs are like a route. You can think it like we will ship them with some means. Maybe a truck is going to go, or like, so basically from plant 1 to region 1, there is going to be some shipment. And then if we do per unit, we are going to pay 131 monetary units, basically. If we ship like 10 units from plant 1 to region 1, then we are going to pay like 1,310 monetary units. Right. So basically each of these on the arc is a cost. And the idea is like plants, basically, it seems like there's a capacity limitation, like this plant cannot ship more than 450 units. And this is a very common thing, right? The warehouses or the plants, they have certain number of people or certain number of, like the trucks that they can ship out in a certain day. So which means that they cannot do more than a certain amount, depending on how big the plant is. Or maybe there's some limitation, because they cannot store more than a certain number, because the plant 1 maybe is smaller than plant 2. So regardless of the reason, this is a very common case that the origin node or the node that we will ship from is going to have some constraint on how many they can ship. So then the question becomes like, how can we fulfill this 450 units of demand in region 1? Okay, and then how can we ship to fulfill these 200 units of region 2? So these are kind of different demand constraints here. So basically this table here that you see became this nice network form, like when you start reading the problem and writing it. And I think this makes it very clear. Now the decision variable here is like how many units to ship from this node to that node, to this node, to this node. So basically how many is to ship on each arc. Okay. And this is actually, this is usually in a multi-echelon supply chain systems or supply chain networks. This is what happens, like this is a multi-echelon, right? You have one echelon here and then the other echelon here. And sometimes, companies have even more. And then they try to determine how many to keep in each of these nodes and then ship. So now we will solve this problem. So here, basically, we want to minimize the cost. while we are not violating the capacity constraints, and then while we fulfill the demand here. Okay, so I'm going to open the Excel for this. Let's open. I think this is the one. Okay. Okay, and again, this file is uploaded. So under module 2, under the lecture note, and let me show you where it is. Like if you want to kind of follow through, you can see that right now we are going through this lecture 6 notes, and underneath we have a bunch of files, and these are the files basically I am sharing with you right now. So the one that we are looking at is this one, which is transportation alternative. Okay. And we will go through the SAS as well, but I think Excel is quite helpful for this problem. So let's go through that first. So here the decision variable is flow. So I'm going to actually remove the decision variable here. Okay. So basically we need to determine how many units, right? What is given to us is the cost. So from origin 1 to destination 1, the cost is 131. From origin 1 to destination 2, the cost is 218. From origin 1 to destination 3, the cost is 266. Okay, so basically these are like the costs that are given on the arcs. And what it is asking us is like how many units here, how many units there. So how many units to flow from 1 to 1, like origin to, you know, like origin node 1 to destination node 1. Right? This is going to be our decision variable. The cost is going to be the sum product of these two columns. Because for each unit we flow, there's a cost, right? And the cost varies based on the arc. And basically the arc, and once we solve this problem, it's going to basically tell us what's total cost, right? This cell. And then we need to respect the optimization, the constraints and restrictions that are given to us. So here, the first constraint was about the capacity of each node, origin node, right? This tells us the outflow from origin 1, because origin 1 to destination 1, origin 1 to destination 2, origin 1 to destination 3, origin 1 to destination 4, they're all flows out of origin 1. So then the summation of this is gonna be the total flow out of origin, right? And then they need to be below 450. This is a constraint given to us. And then the same constraint applies to origin 2. And then the same constraint applies to the origin 3, but then they all have different right-hand side, right? Because different capacities. Basically, this may be because the plant 1 is smaller than plant 2, maybe. This is why the capacity of plant 1 is less than plant 2. This is the capacity constraint part. Now there is a demand constraint as well. So the demand constraints are going to be such that we need to fulfill at least that much of demand. Okay, so basically region 1 has a demand. So whatever inflows into region 1 needs to be greater than equal to 450 so that we can fulfill the customer demand. Okay, so this tells us basically the inflow into region 1, because region 1 can accept from plant 1 or plant 2 or plant 3. And then when we sum them, that tells us the total units inflow to region 1. And then the constraint becomes the total inflow, whether it is greater than or equal to 450, which is demand given to us. Okay, and then the same thing we do for inflow into second node, inflow into third region, inflow into fourth region. And all of them needs to be greater than or equal to the demand that's given. And that's all. So basically, this is all the things that we need to enter here. And now we are going to hit the solver. Okay, let me make it a little small so that we can see the solver button. When we hit the solver, objective function is B19. It's given here. decision variables are the floats, right? We talked about that. And then the constraints, basically, these are the, these last three are the capacity constraint, because G6 needs to be less than I6, G7 needs to be less than I7, G8 needs to be less than I8, right? It gives us this. And then the other ones, right? And again, just to make sure you guys remember, we can actually add more constraints, right? I can say add, and then I need to just tell the left-hand side, right-hand side, and the relationship. And for example, if I want to add this one again, then I'm going to say left-hand side greater than or equal to right-hand side, and then I'm going to say, okay. Now that constraint right now is added. So we should have 2 times the same thing, like here you can see. So I'm going to just delete them because there is no point of having 2 times, right? And then we will make sure that we have the non-negativity checkbox checked. And then we just solve this. Like, once we solve it, basically, it's going to tell us how many units that we should flow, you know, like from each of these. And we can look at, we don't need to look at the sensitivity here. We can just say, okay. Okay, so you can see that this is basically the output from the solver. Before we hit the solve button, it was all 0 actually. Once we hit the solve button, basically it populated these numbers. Okay, so basically, I think the challenging thing about this problem is actually modeling it right. Like when you read the problem, like there's a network optimization and there is the origin and destination. How are you going to put each of these constraints and you know, like capacity constraints, demand constraints, the cost in one form, right? I think that's the challenging part. So again, what I would recommend, you have this solution here, right? You can always listen again, but I would recommend you follow like the step by step. For example, first define your cost parameters and define your decision variable and see whether you do it right. And then add the constraints one by one, and you know, like you can solve it actually and try at each step what the results are. But I would recommend you, I think here the challenging part is basically the modeling, you know, like making sure that your model is right, and then you input it to the Excel in the right way. Any questions? Okay. So, so this is how you solve it in Excel, right? And then we will do the same thing in SAS. And SAS is going to be a little different, but let's see how it goes. Okay, so I'm going to just close this one. Okay, so the problem that we are going to solve is this transportation with ARC network. And again, if you want to have a look at it yourself, it is, again, we are under module 2 still, right? And then under module 2, you have all the files that I'm sharing. This is the PowerPoint, the deck that we are looking at right now. And then these are all the files. And then the file that I'm going to walk you through is like transportation with ARC network. So we looked at the same problem with this Excel file. Now we're going to look at the SAS. Okay. I think with SAS, here the challenging part is going to be the sets. So there is going to be, you know, like I'm going to kind of emphasize that more and then spend more time on that. Once you understand the sets, I think it's actually, I think it's easier actually to model in SAS than Excel. Because SAS, basically everything is more straightforward. In Excel, there are too many cells. You add this, you remove that. You know, like Excel becomes, as your model gets more complicated, Excel becomes more error prone. So I would recommend basically spend some time on the sets in SAS, and I think that will help you a lot. Okay, so again, same as before, we are going to run PROCOP model. So between PROCOP model and quit, our code is in between basically. And so we have 2 sets, right? We have the origin indices and destination indices. So we have 3 origins. These are the plants, plant 1, 2, and 3. And we have 4 regions, which are the destinations. So I'm defining kind of 2 sets basically. And between curly bracket, whatever you put in becomes the index for your set. Okay. And then arcs become the cross product or Cartesian product of those 2, right? Because each origin to each destination, there's an arc. So after we define origin and destination, we define an arc set, but then arc set, we don't need to put one by one. We can just say origin, cross, and cross here is part of the syntax and destination. And once you do that, each origin is going to have an arc to each destination. Okay, so basically, and let's see whether we can, see what it looks. Okay, I'm gonna just print what the arc looks. Because I think for this problem, this is the most complicated part. So I'm gonna clean, so the way that I clean my log is like I just hit here and then hit the, like the clean page here, and then it kind of cleans it. Okay, so the first thing I wanna do, actually, I wanna just see whether this statement is gonna work or not. Let's see. Okay, it does. So let me clean again, and I'll show you what I did. So basically what I wanna do is I wanna look at to see what is origin, what is destination, and what is the arcs, right? Okay, so one way to run code like partial code is you can just select and then just hit the submit. Then SAS is gonna just run the selected portion of the code. And I do that sometimes when I wanna see what the output is gonna be like step by step. So basically I'm gonna hit this. And you can see that the origin set is like 1, 2, 3. Destination set is 1, 2, 3, 4, right? Which makes sense. But the arcs actually is like 1 to 1, 1 to 2, 1 to 3, 1 to 4. 2 to 1, 2 to 2, like it's like the cross product, right, of 1, 2, 3 with 1, 2, 3, 4. Okay, so this is an easy way kind of to define the index set for the arcs. You can also define them as same as here, you can actually put 1, 1, like I can actually copy this, and then I can put, instead of doing a cross product, another option is like running it like this. And this is fine too. So instead of basically having this origin cross destination, which is a shorter form, you can actually explicitly put everything one by one, right? But one of the things that I want to emphasize in this lecture, because this is a more advanced class of optimization, is instead of writing things one by one, it's better that you write in a more concise form, especially in the industry, because the problems are going to get bigger, the problems are going to get more difficult. So then it's better to keep your code and data small as possible. Okay, and then the next thing that we want to define is the cost, right? Cost is a parameter like an input. So basically, cost is going to define over arcs. And what I did, I just actually copy paste, like for the first set of arcs, right? We have this cost. And you can see that the first row actually is exactly these numbers: 131, 218, 266, and 120. And then the second row is here, and you have exactly the same numbers. So basically, we define the cost like this, like one by one. You can again read it from the data, but I thought that would be too advanced for this example. You can, like copy paste still like this. But what you need actually, you need one cost parameter per arc element. Okay. So this basically, up to this point, what we did, we defined the index sets, right? And then we defined the cost parameter. The next thing we will do is actually we will define the capacity and demand, and then we will run the optimization problem. Okay, capacity here is defined over origin, and demand is defined over destination. Because each capacity is defined at the plant level. So we are saying that the first plant cannot ship more than 450 units. And then the second plant cannot ship more than 600 units. And then the third plant cannot ship more than 500 units. And then for demand, it's like there's a minimum demand, right? We say that the region 1, we need to fulfill at least 450 units. And region 2, we need to fulfill at least 200 units. And you can actually see the pair here, right? These are the demand constraints defined here. And these are the demand parameters, same as here. Let me put side by side. Okay, and then, so this is the parameter part. So we define the index, we define the cost, capacity, and demand. So those are 3 parameters, right? So we have 3 sets: origin, destination, and arcs. We have 3 parameters: cost, capacity, and demand. Now, next step is defining basically 3 more things: decision variables, objective function, and the constraints. So decision variables are basically I define as x. X is the flow. So for each arc, we need to define a flow. Okay, so basic arc here from 1 to 1, 1 to 2, right? Each of them. And this is in Excel how we did it. Like from origin to destination, that's one arc. And here, this is the flow, which is the decision variable. And here we define it with the var statement. And I gave the name X. You can give anything. You can give flow or, you know, like different things, but you can give any name. And this is defined over arcs. And then the next step is define the objective function and then the constraint. Here, the objective function is basically the flow multiplied with the cost. And then the capacity constraint is basically the flow from the destination less than equal to the capacity. And then the demand constraint is flow into an origin or a region, right? Flow from the origin to each of the region, the summation of that needs to be greater than equal to demand. And then you just solve this problem basically after that. And then let's solve it. Okay, so the solution is here. So this is the plants, these are the regions, and then this tells us the flow between them. Okay, so this kind of concludes our third example on the network optimization. So we basically, to recap, we went through 3 different examples. So this course, this lecture's topic was advanced optimization, right? We went through some applications, like real life applications. We talked about the employee scheduling. We talked about the product mix. And then we talked about the network optimization. And each of them basically is a little bit more advanced than what we did. So this gives you a sense of how you can use these optimization tools, right, in different areas. So this kind of concludes the notes for this class. But I want to kind of emphasize a couple of things. So our test is coming. Like our test, I think, is in 2 weeks, October 10, right? And it is going to basically be on chapter 10, 11, 13, and 14. So it's going to basically cover forecasting, regression, and optimization. And I think homework 1 and homework 2 are great. CCPs are great. And I'm going to actually do a review next week. Basically, next week's class is going to be an exam review, like the review of the lectures. And if you have any questions, anything. So if you have any questions, please bring them. So we will basically talk about the topics that will be covered in the exam. I'll have a couple of things that I want to cover, but then at the same time, if you guys don't have questions, we are going to cut it early. So basically, let me maybe think about what questions you have for the exam. Basically, next class is exam review. And that's it. Any questions? Great. So thank you so much. Talk to you guys next week. By the meantime, if any questions, please let me know. And again, next week, we are going to do exam review. Bye.